When I let go of these two balls, they're both going to experience something called free fall, which is falling at the force of gravity. And since acceleration due to gravity is the same everywhere on Earth, negative 9.8 meters per second squared, they will fall at the same time. However, because they have different masses, the force will be different because of Newton's second law, which is force equals mass times acceleration. But we're going to demonstrate how they fall at the same time. Look at that. Wonderful. So you just watched an acceleration due to gravity, which therefore made free fall, and the force due to gravity. But now I'm going to apply some force, which will increase the acceleration of the objects and therefore increase the net force that they experience. So if I throw these down, I'm going to apply a force. And one of them fell more quickly than the other.
As I'm hanging here, I have potential energy within me, but if I were to drop, I would then be filled with kinetic energy. And the sum of those two energies makes mechanical energy.
While Diana was running, her pushing into the ground with her foot propelled her off of the ground because of an action-reaction pair that goes with Newton's third law. The resulting acceleration and linear velocity gives Diana momentum and inertia. And by Newton's first law, when she lands in the sand, an external normal force pushes up against her downward inertia, which stops her motion. And the change in her momentum from the running to now stopping is her change in impulse.
Sorry to interrupt, Natalia, but I couldn't help overhearing you guys talking about momentum and impulse. So, in an elastic collision where two objects come together and collide, there is a conservation of momentum, but not a conservation of kinetic energy. In elastic collision, there's a conservation of momentum and a conservation of kinetic energy. And that can be seen when two objects come together and then bounce off of each other. Now back to you, Natalia.
If I were to run around this track, I would travel a distance of 400 meters, but my displacement would only be 0 meters because I would end in the same place I started. So when I roll this ball off of this horizontal surface of the mat onto the ground, when it's traveling in the air, it'll be experiencing horizontal projectile motion because the only force acting on it will be the force of gravity. And then when it hits the ground or the track material, because this certain material has a low coefficient of friction, it will therefore have a low force of friction and the ball will keep rolling after it's rolled off the mat. So here we go. So now the same thing, it's experiencing horizontal projectile motion when I roll it off the mat, but now it's going to land into grass, which has a higher coefficient of friction than the track material did, so therefore the ball will stop rolling earlier because the force of friction from the grass will be greater. Kinematics is a study of how objects move, and a big part of that is projectile motion. And one type of projectile motion is angular projectile motion, which means that when the object starts moving, it starts at a launch angle and it goes in a parabola. So an example of that is if I set this volleyball, I sent it with a launch angle and then it went all the way over there because of its angular projectile motion.
Oh, hey, didn't see you there. Over here, a door is a great example of torque. See, if you push the door closer to this access point, it's harder to push open the door because it requires more power, requiring more force. But if you push a door right there, you'll have a lot more ease opening it because it requires less work and less power. The right-hand rule can help us understand how torque works in a gyroscope. If you extend your right hand, palm down, curl your fingers downwards, and your thumb out, it helps you to see the direction of each vector. So, a great example of centrifugal and centripetal force can be seen by this demonstration. Say this coin is the center point a car is turning around while going around a corner. The car goes around the corner, and because of the velocity of the car and the people inside the car their body will keep going as it goes around the corner. In this example, the car itself has centripetal force applied to it, while the person in the car has centrifugal force applied to it. Because when the car goes around the corner, the car keeps going in the circular motion, while the person keeps going straight. This demonstration is also a great example of angular velocity and tangential velocity as well. Angular velocity is the rate of change of an angular position of a rotating body. If you increase a joint's angular velocity at any point that is a part of or connected to the rotating body segment, there will be an increase in the linear speed and also an increase in the tangential velocity at any given point. And lastly, this demonstration is a great example of the centripetal acceleration. Centripetal acceleration is the rate of change of the tangential velocity. Consider an object moving in a circle of the radius r with constant angular velocity. The tangential speed is constant, but the direction of the tangential velocity vector changes as the object rotates.